Let's derive the Pythagorean trig identities. So these three identities here, the Pythagorean identities. So first, let's write out the general definition of trig functions. So we've got an xy coordinate plane, and then we think about an angle that's measured from standard position, so meaning the initial side is the positive x-axis, and then the terminal side is anywhere in the plane except the endpoint of the initial side and the terminal side are both fixed at the origin. So let's put the terminal side at any random location in the plane. This line extends out to infinity with endpoint at the origin. This angle is measured in the positive direction, so counterclockwise, theta. Now, next, we pick any point we want along this line. So let's say here. And then from this point, we create a right triangle to where the right angle is adjacent to the horizontal axis. The distance between the point we picked and the origin is the hypotenuse of the right triangle, and we call this the radius. That's always positive. And then the side lengths of the right triangle are represented by the coordinates of the point, x and y. However, what's unique about the right triangles in this general trig function definition is that the side lengths can be negative, right? X would be negative here and y would be negative here. X and y could be negative or positive depending on the quadrant, but r is always positive. And why is r always positive? Because r is equal to the principal root of x squared plus y squared. Okay, so you can see that for any angle, any positive or negative angle, because a negative angle would just rotate clockwise, you can create a right triangle with this, where the side lengths are based purely on a xy coordinate system. And so with that, we define the trig functions so that the sine of theta, and this is valid for any theta in any quadrant, what was just set up here is completely general. Sine of theta is y over r, but sine of theta could be negative depending, in the third quadrant, sine of theta is negative because y over r is negative, right? Okay. Cosine of theta is x over r, and tangent theta is y over x. Okay, and cosecant theta is r over y. Secant theta is r over x, and cotangent theta is x over y. Okay, so now with this general definition, we're going to use the Pythagorean theorem to derive the Pythagorean identities. So the Pythagorean theorem for any angle theta, any angle, is x squared plus y squared is equal to r squared. So from here, let's divide this entire equation by r squared, and we get x squared over r squared plus y squared over r squared is equal to 1. Now, with properties of exponents, we can write this as x over r squared plus y over r squared is equal to 1. But what is x over r and y over r? That's sine theta and cosine theta. So we've got sine squared theta plus cosine squared theta is equal to 1. All right, now let's start back with just the Pythagorean theorem, and we're going to divide both sides by x squared now. So this is x squared over x squared plus y squared over x squared is equal to r squared over x squared. So this is 1 plus y over x squared, which is equal to r over x squared. Now, y over x is equal to tangent, and r over x is equal to secant. So this is 1 plus tangent squared theta is equal to secant squared theta. There's the second Pythagorean identity. Okay, now we come back to the start of the Pythagorean theorem again, and we're going to divide both sides by y squared. Okay, so we've got so this is x over y squared plus 1 is equal to r over y squared. X over y is cotangent, r over y is cosecant. So this is cotangent squared theta plus 1 is equal to cosecant squared theta. And there's the third Pythagorean identity.